Okay, so then we start the new chapter. So this is the function space, etc. So a function space. And then several other things. Okay. Now you remember that. Sorry.
I'm going to take.
You okay? Take it. Yeah. Okay. Well, by the time they come, if you have any questions on the last, they're already here. Okay. No. If you have any questions on the last chapter, maybe we can discuss that. Or what we can do is the following. So you know that the exam will be on 8th. 8th, yeah, right. So next week I will not be here on Tuesday. So Thursday, okay, I'll have the lecture. But if you want, we can. I mean, this week you can go through the first 2 chapters very well, and then you can maybe ask me questions on Thursday before we start actually continuing this. Maybe half an hour we can spend on if you have any questions. No? On Thursday. So okay, let me now just start this. Okay, so this goes back to the first chapter actually. In the first chapter we discussed, remember, the vector spaces, and one of the examples I gave you was also the functions. The space of functions is also a vector space under the rule of addition, pointwise addition, and multiplication pointwise by some numbers, right? So those are vector spaces. So this function space, so let me again, so let's for definiteness, let's take x in some interval a to b. Okay, there is some interval. I will take finite interval to begin with. So this a and b is a finite interval. Okay, and consider the function f of x, where x belongs to that. So this is some continuous function. Now you can define the additions. Suppose f1 and f2 are 2 functions, then you define f1 plus f2 of x as simply f1 of x plus f2 of x. So it's just a pointwise addition. At each point, f1 and f2 have some particular value, right? You just add the 2 values, and that defines to you a new function. So I mean, just to remind you, so suppose the interval is something like this, a and b. And f1 is some function here, and f2 is, let's say, another function here. Then f1 plus f2, you just add them up. At each point, you go up and see what is the value of f1, what is the value of f2, right? And then add this up. So it will be something here. And then you do that at each point. So there will be some points like this, and then you join them together. So that will be f1 plus f2. So it's pointwise addition. And similarly, if you give me some number alpha, then alpha is some number. Okay, alpha times f is again another function which is simply defined by alpha times f of x. Okay, so f of x is some value at a given x. You just multiply that number by alpha, right? Again, you can plot that new function. That is the definition of alpha times f. Okay. Now, of course, for quantum mechanics applications, we'll be mostly considering complex vector spaces. I mean, so complex functions, these alphas are also complex. But if you can also consider real cases. I mean, so it's up to you. I mean, you can either choose real functions or complex functions, right? So I will be very general. I will just take it to be complex functions. Real is a special case of that. Okay. So under this rule of addition and multiplication, this is a vector space. So let's say, what shall I call this space of continuous functions is a vector space. I have to also specify to you what is the 0 in the vector. There is a notion of null vector. So what is the 0? The null function. The null function is simply 0. At every point, it just gives you 0. Okay. So the null function at any point x is equal to 0. That's a definition of null function. So this completely, so all the requirements are there. I mean, you can easily check that all the definitions that you saw in the first chapter for the vector space, that this will satisfy this rule of addition, multiplication, and this definition of null vector. Okay. So it's a vector space, okay. Right? But this is an infinite dimensional vector space. So this was an example of infinite dimensional vector spaces. Now, in the first chapter, although we discussed some of the things in generality, like for example, this notion of inner product, what's Cauchy-Schwarz inequality, all those things were in general. Okay, but later on, when we went to the eigenvalue problems and so on, and the detailed analysis of the diagonalization issues, we went to the finite dimensional cases, right? Okay. Now, there are some subtleties when we discuss infinite dimensional spaces, and we'll see that here, right? So I remind you that in the finite dimensional case, so this is going back to the first chapter that we discussed. So in the finite dimensional cases, right? So I mean, if you can choose some, let's say you can choose some basis, and in particular you can go to an orthonormal basis, right? So you can choose, let me call this basis as EI. These are the orthonormal bases, I going from 1 up to n. So it's an n-dimensional space. So there are this basis here, and then any vector f can be expanded in terms of this orthonormal basis. So this is, I should say, orthonormal. Okay. You can just choose this basis, some coefficients, let's call it fi ei, right, summed over I. Okay. Now, what is the important point about this is that this space is closed for the finite dimensional case, and I will define to you what I mean by closed. It is closed in the following sense. Suppose, so the finite dimensional, let me call it finite dimensional vector space V. So V is closed in the following sense. So suppose I am given a sequence of vectors, f1, f2, fn. Okay, it's an infinite sequence of vectors. Okay, and it's such a way that if you take you remember I defined to you the distance, the distance function rho. Do you remember that? So suppose it's rho. This sequence is such that the distance between fn and fk, say fk and fl, goes to 0 in the limit k and l go to infinity. Okay, so this is a sequence which has this following property. Okay. What it means? It means that if you go sufficiently far away, I mean large values of these n's, then the distance between those functions become very smaller and smaller and smaller. So in the limit when k and l go to infinity, the distance becomes 0. Okay. So in such cases, you would imagine that there should be a limit vector, right? So, and indeed it is the case that in this finite dimensional vector spaces, that there exists a limit vector f. Okay, there exists a limit vector f, such that rho of so what we're saying that in this case, so fn in the limit n goes to infinity gives you a vector in the original vector space V, such that of course rho of f with fn go to 0 as n goes to infinity. I mean, this is not difficult to show, but I mean, I think it's more or less is obvious, right? I mean, this kind of thing you already know for the numbers, right? If you take a sequence of numbers, then if the distance between instead of vectors, imagine it's a numbers. Numbers is just a one-dimensional vector space, right? If you just take these numbers, and if those numbers satisfy this condition that the distance, the difference between the numbers, the modulus of the difference between the numbers go to 0 as you go far away, then that sequence converges to some number, right? So this is exactly the analog of it. Now it's an n-dimensional case, so you see you can formulate it in terms of this n numbers, right? Right, and the distance. So I mean, so in other words, I mean, let me just motivate this point. So I can expand each of these vectors in terms of this orthonormal basis, right? Each of these vectors. So in general, some fn vector will have, I can expand in terms of again the basis vectors, right? These are the expansion coefficients for this particular vector, and since these coefficients will be different for these different vectors, I should remember which vector I'm expanding. So that's why I put the n there. So then what will be this the difference? You can immediately work it out. It is simply maybe I should erase this part here. Right. So if I compute this difference, what is this? This is nothing else but fk. The distance, remember, was defined like this, right? Fk minus Fl with Fk, the inner product of this vector with itself. This was the definition of rho, right? Rho of Fk Fl is simply I mean, this is, I'm just trying to remind you of the first, maybe you've forgotten some of the things from the first chapter, but just, so this is the length rho square, let's compute a rho square, the length square. Length square was that. Length itself is the square root of this, but let's take the square of it, rho square, okay. And then, so this will be, you can just expand it. So what is this object? This object is nothing else but Fki minus Fli EI, right? This object is because each of them has the expansion. Okay, so when I take the inner product of this vector with itself, you will find that this quantity is nothing else but Fki minus Fli mod square I going from 1 to n. Right? I mean, here there is a summation, where I've used the fact that these are orthonormal, right? So you'll just get that. So what we are saying is that this tends to go, this goes to 0 in the limit k and L goes to infinity. But you see, that means that each of these terms goes to 0, right? Because after all, it's a sum of positive numbers. These are all non-negative, right? Modulus square. So each of them is some positive number. And we are saying sum of these positive numbers goes to 0, which means each of this positive number must go to 0, right? So each of these numbers must go to 0. For all I. For every I, this should happen. But then these are just complex numbers. And you know that when a sequence of complex numbers satisfy this condition, then that converges to some complex number. Okay? And that complex number will be the expansion of this f in the orthonormal basis, the expansion coefficients. Okay? So in other words, so this will converge to some number. So this implies that the sequence of these numbers will converge to some number fi, right? And then f itself, this vector f, is simply given by fi ei. Okay. Summed over I. Okay. So this is basically guaranteed to you that I mean, it's so in this case, so it's closed in the sense that if there's a sequence which satisfies this condition, then there exists a vector in the original vector space to which this sequence converges, right? However, this is no longer true when we discuss the function space. Okay. So I just give you an example. So this is a subtle point that I mentioned, that some of the things you cannot carry blindly from the finite dimensional case to infinite dimensional cases. Okay, and this is one point which you cannot carry. So let's see. So remember again, so we define the S as a space of functions, continuous functions. Okay. Perhaps I should maybe first, before that, I should define some scalar product. Yeah, so let me first define the scalar product. I mean here, okay, so to be very concrete, I'll define some scalar product. So a space of continuous functions in the interval for on the interval x belonging to some a to b. Functions of x belonging to that. So this is my space, and I have to define, first of all, I mean, to discuss all these things, to discuss a distance function, I need to define, I mean, I need to define what do I mean by distance, right? So let's define, so suppose f and g are given, f of x, and I will many times, since it's a vector space, I will many times use this notation, this bracket notation for that. I mean, this just means if it's a function, right, in this particular case. So if I'm given two objects, so f of x and g of x, two functions, which is continuous, then I can define what I mean by fg is simply the integral complex conjugation of f bar of x, g of x, and some weight function f of w of x dx from a to b, this integral, where w of x is called the weight function, has a property that this is strictly greater than 0. I mean, it's non-negative, it's positive everywhere, it's positive in this interval, and it's called, this w is called the weight function. Okay. It's a, I mean, it's just, you can choose w equal to 1. Okay, that's a very simple example, but we keep it generally because you know that in many physics examples you do have non-trivial weight. I mean, not just weight is not equal to 1. For example, if you go to the three-dimensional space, right, and you go to the, suppose you look at the spherically symmetric functions, okay, then if you, so if I just take, this is a side remark, so suppose I just take a spherically symmetric, so in three dimension, consider the functions which are spherically symmetric. Actually, one doesn't have to choose spherically symmetric, but okay, let me just, for simplicity, let me choose spherically symmetric functions. And then if I define, so f of x and g of f bar of x and g of x integral d3x, right? This will be the natural inner product in the three-dimensional, Euclidean three-dimensional space, right? But then when you go to the fact, use the spherically symmetric property, then it's better to go to the polar coordinates, right? And once you go to the polar coordinate, d3x becomes r square dr sine theta d theta d phi, right? This probably you know. Where theta and phi are, I mean, phi is the azimuthal angle, theta is the angle between the north pole. You know, these are the usual radial decomposition. But now because these functions do not depend on theta and phi, this you can integrate, and that just gives the area of the unit sphere, right? So this you can get rid of, it just gives you some number, right? And then what is left over here is the f as a function of r, because it only depends on the radial coordinate, complex conjugate g of r, integral 0 to infinity, right? But now you see there is a non-trivial weight function here, right? So to be able to discuss all these possible situations, we just keep an arbitrary weight function, okay? So now it's a very general thing. I mean, you can, in some cases w is 1, in some cases w is not 1, but important point is it must be not negative, it must be positive. It will take it to be strictly greater than 0 everywhere. Yeah, I mean, we'll take that to be, yeah, strictly greater than 0. Whatever the w is, I mean, whichever problem. I mean, here, of course, it goes to 0 at r equal to 0. It's a limit point, I mean, one of the end points. But everywhere in the interior, it is not 0. Okay, you can check that this definition of the inner product satisfies all the properties that we have listed in the first chapter. Okay, linearity in G is very clear, because I mean, it's linear in G. It's antilinear in F, as was in the inner product. Also, let's see, what was it? There was one more property which was, yeah, f with f itself is, I mean, if you take both of them equal, same vector, then it was non-negative, right? So f with f, which is of course clear because it becomes f mod square. If g is equal to f, it becomes f mod square. So that's positive. This is positive. Everything is positive. So you're integrating a positive quantity. So it will never become negative, right? That is also clear. And finally, there was also the statement that if f with f is 0, then f must be 0, right? Which is also clear, but because if for this to be 0, the mod square itself must be vanishing because this is non-negative, right? So therefore, the function will be 0. So all the properties are satisfied by this definition of the scalar product. In fact, this is what you have been doing in quantum mechanics, right? In one-dimensional quantum mechanics problem, this W will be 1. In three-dimensional quantum mechanics problem, it will be this, right? And then, okay, if you wish, you can go to the spherically symmetric case or something, then it will become that, etc. But this is the standard, I mean, this is a natural inner product that you would define. Now, the problem here is going back to this issue of the subtlety. So, okay, sorry. Once again, I mean, once the inner product is given, you can define the distance function rho as usual. So, therefore, we can define rho of f and g, the distance between f and g, which will be simply, I mean, this is nothing else, but let me define a rho square. Otherwise, I have to write square root here. This will be simply the integral f minus g, fx minus gx mod square wx dx, right? That is the, I mean, just right? Just you use this basic definition of this distance square. Okay. So now, let's suppose I'm given a set of functions again, fk x. This is a sequence, which again satisfies this criteria that rho between fk, sometimes I use this notation, okay, let's like that. So of fk and fl goes to 0 for k and l sufficiently large. So suppose I'm given a sequence of functions, okay, which satisfy this property, where the distance function is simply given by that. Then question is there a vector to which it converges? Is there a function to which it converges where that function belongs to this original space, which means the space of continuous function? Okay. The answer is in general is not true. Okay. So I'll just give you an example of that. So consider, in fact, the example is given here. I mean, there are many examples, but okay, I'll just write down this example here. So consider this function f of kx. So you might take the interval to be from -1 to 1. So a and b, I take the interval to be -1 to 1. A, b is -1 and 1. Okay. And I define the function f of kx as it's 1 when x is between, I mean, less than 1 and all the way up to 1 over k. Okay. It's kx plus 1 divided by 2 when x is between -1 over k and 1 over k. Okay. And finally, it's 0 for x less than -1 over k, all the way up to -1. Right. So it may be better to plot it instead of, I mean, this doesn't tell you much. I mean, looking at it, it's not so obvious what is happening. So let's plot this function. So here you have x is 0, here it's 1, let's say, and x is -1 here. This is the x, and I try to plot it. So up to, so let's say k is some integer, right? I mean, k is some, it's a sequence. I'm considering sequence of functions, k equal to 1, 2, 3, all the way. So take any number k. So now this is from 1 over k up to 1, right. So 1 over k will be some number, say this is 1 over k. Okay. So for example, this is roughly like k equal to 5, for example. So this is 1/5. Okay, whatever. So now from so this is say 1 here. So from 1 over k up to 1, this function is 1, right. So this comes, I plot it like that, right. It's equal to 1 in for all these values of x. Similarly, from -1 to -1 over k, so this is -1 over k, this function is 0, right. So this stays 0 here up to this point, and between this and this, it's a straight line. You see, notice that this, let's evaluate this at x equal to 1 over k. When x equal to 1 over k, this simply is 1, so that's the same value as that, right. Similarly, when x equal to -1 over k, this becomes 0, so that's that. So that's why it's a continuous function. So I mean, so you just draw a straight line. Okay. So this is the way the function looks like. Now, of course, if you increase the value of k, this 1 over k is going to become closer and closer to 0, right. So this is going to become more and more, and in the limit k goes to infinity, it's clear that this point will shift there to the 0. So this function will be equal to 1 all the way up to 0, whereas here it will be all the way to the function will stay 0. So in the limit, the function that you get is a discontinuous function. You see, every function is this is continuous, because you see there is continuous. It's not differentiable here, but I don't care. I mean, I'm just talking about continuous functions, right. In fact, you can easily construct even a sequence of smooth functions even. I mean, as an example, okay, let me first, I'll get to that. But so now in the limit as k goes to infinity, what's going to happen that this function will look like this will become a discontinuous function. It will just stay like that, and then suddenly it jumps up and then goes like that. This is a step function. This is called a step function. Okay. So here you have a situation where the sequence of the function, the limit of the sequence is not a continuous function, therefore it is not in the original space, right? Sorry.
I would like to know definition of rho with integral. Say the same in the other espace or just l'espace integral.
Sorry, repeat that again. I start this 0.
No. Phi.
Rho. Okay.
Yes.
Yeah.
Definition of rho.
Yeah.
With integral. Okay.
Yes.
Okay. I would like to know this definition stay the same in all espace or just espace integral.
This is the, I mean, so I started with the vector space of this continuous functions, right? Then I want to define some inner product, right?
So in other space, when I want to define rho, I write rho equal integral phi de x minus g de x modulo carré.
Mod square.
Other space, the same definition.
Same definition, yeah. I mean, for different spaces, the w may change, right? I mean, so here we are considering functions of one variable, right? So let's say if I consider functions of one variable, so what can change? You have the interval can change, right? Or the weight function can change, right? So those will define you different possible scalar products, no? Distance, right? Yeah. In fact, we will construct many examples of it with different weight functions and so on and so forth. No? But at the moment, I'm just giving a general discussion. Yeah. Now you can see. So, for example, for this case, let me just take a simple w of x equal to 1. For this example, let me just take w of x equal to 1. You can immediately see that fk. I mean, if you take the distance function rho of fk and fl, this goes to 0 in the limit k and l go to infinity, right? That is easy to see because let's say, so we'll want to take the distance between these two, right? And let's assume that k is smaller than l, right? I mean, k and l are different. They have to be different, otherwise it's 0 anyway, right? If the same vector is there, the distance is 0, right? So let's take k and l to be different. So okay, one of them has to be greater than the other, right? So let's take k to be less than l. Okay, so fk looks like this. How will fl look like? Fl will start with the 1 over l here. I mean, right? Since l is bigger than k, 1 over l will be smaller than 1 over k, right? So fl function will be looking like this. It will go all the way up to this, and then a straight line down to minus 1 over l, right? This is how fl will look like. Now, if I take the difference between fk and fl, you see it is 0 everywhere outside this 1 over k and minus 1 over k, and it is non-zero only in this region, right? How much it is? It's just a difference between these two functions, which is something here, right? Right? Whatever it is, it's smaller than 1. The difference is smaller than 1. Okay. So if I compute this mod square fk x minus fl x mod square dx, remember I chose w equal to 1 for simplicity, although it doesn't have to be. So minus 1 to 1. This is my distance function. But you see this integral, I mean from here onwards this difference is 0, from here onwards it's 0. So it's actually effectively reduces to minus 1 over k to plus 1 over k, because outside it is 0, right? And then, and inside this region, anyway the difference is whatever it is less than 1, right? So this quantity is going to be less than, this quantity is going to be less than if I just replace this by 1, right? Because anyway it's positive quantity, mod square. So this, sorry, this is rho square, okay? So this is, so I can, this is going to be less than if I just replace this by 1, right? But when I if replace by 1, the result of the integral is simply 2 divided by k, the length of this interval, right? So you see as k goes to infinity, this distance goes to 0, right? So indeed, I mean this satisfies all the Cauchy criteria for the convergence, except the problem is that it is converging to a function which is not continuous. So it is not an element of your original space, right? So therefore, I mean this space is not closed in the sense we are using the word closed. So closed is actually a standard notion. In fact, I mean you have a closed region means that every limit point of that set. If you have a closed set, then every limit point of that set must also be inside the set, right? That's the meaning of closed. So in the same sense, it's closed or not. So this is not closed. Okay. So there is a problem here. Before you might wonder that whether this is because this is happening because I chose continuous functions, but they are not differentiable, right? I mean at this point there is a sudden, I mean the slope changes discontinuously, but this has nothing to do with that, because you can consider instead of this sequence, you can consider another sequence which is like the following: fk of x, I mean let me call it gk of x, equal to tan hyperbolic kx plus 1 divided by 2. Okay, you can choose that, for example. Okay. Now you know tan hyperbolic is sine hyperbolic divided by cos hyperbolic, right? So remind you the definition of sine hyperbolic of x is e to the power of x minus e to the minus x divided by 2, and cos hyperbolic x is e to the x plus e to the minus x divided by 2, and tan hyperbolic is simply this divided by that. Okay. Now the property of, I mean, if you look at this sine hyperbolic divided by cos hyperbolic, and imagine this argument goes to plus infinity, whatever this argument x, let's say, it goes to plus infinity, what is going to happen? This is going to dominate compared to that, right? So I can, in the x goes to infinity limit, this I can ignore, so it just becomes e to the x divided by 2, whereas also the cos hyperbolic x the same thing, e to the x divided by 2. So tan hyperbolic x, I mean tan hyperbolic x, I mean let me use y here, not the same x. Okay. So what we are saying is that tan hyperbolic y, which is by definition e to the y minus e to the minus y divided by e to the y plus e to the y, minus y, this goes to plus 1 when y goes to infinity, plus infinity, and when y goes to minus infinity. You see, when y goes to minus infinity, this will be, I mean, this will dominate, right, compared to that. So you can ignore this. So this becomes minus e to the minus y, and this becomes plus e to the minus y. So ratio is -1. Okay. So this goes to -1, kind of hyperbolic. So now let's go back to this problem here. When k becomes large, okay, this argument is very large, even for small values of x, right? It starts becoming very, for any fixed value of x, keep x, no matter how small, okay, you can go to sufficiently large value of k such that this argument becomes very large. So in that case, this will just become 1, right, for positive. So it becomes 1 plus 1 divided by 2, so it's 1. Whereas if x is negative, right, in that case this will become -1, and that becomes 0. So again, you see this is the same. The limit in the k goes to infinity limit, this function will again become, this sequence will again become the step functions. Okay. So, but this is completely smooth. I mean, it's differentiable in any number of times, right? I mean, if for a finite k, the function will look like this. I mean, it will be smooth. It will look like, I mean, it will not exactly reach 1, but it will be something like this. And as you start increasing the value of k, this will start becoming sharper and sharper. Okay. And in the limit k goes to infinity, this will just become step function. But it's in between, it's all completely smooth, differentiable any number of times. Okay. So this is the problem. So I mean, what to do with this kind of situation? I mean, what this means is that if I want to have complete space, closed complete space, where every limit of every sequence which satisfies this Cauchy criteria is also an element of that set, then we are unfortunately forced to include also non-continuous functions in my original space, right? And perhaps, I mean, okay, this was just an example where the only thing that happened was this kind of a step. But you might imagine there are situations where huge numbers of discontinuities may happen, right? So in such cases, how do you handle? I mean, how can you define the inner product? Because inner product was defined by this integral. And the integral was defined, of course, by the Riemann definition of integral. You remember how you define this integral? You divide the interval into small pieces, and then you remember the definition of Riemann integral I gave you, right? So this was that basic idea. You just divided the interval a to b into n number of pieces, and then you sum up this the integrand evaluated at some point in the, you choose arbitrarily some point in the, let me just remind you, the Riemann integral. The definition of it's a Riemann integral. Was simply defined as, so I have some interval a to b, and what I do is I just divide this into large numbers of subintervals, right? And then here's my some function. Let's say some function is there, whatever. So I will just, and I choose arbitrarily some points inside each interval. You evaluate this function at that point. So let's say psi I, psi 1, psi 2, these are the points in each interval. So then you evaluate f of, if I want to integrate, let's say f dx, f of x dx a to b, then that is simply given by taking the limit n goes to infinity, where n is the number of intervals, okay, and the sum of f psi I times delta xi. Okay, delta xi is the length of that ith interval, okay, and summed over I going from say 1 to n. This n intervals, right? This is how you define. So if so this is defined if the limit exists, right? But if, I mean, you would imagine that if the function is continuous, it doesn't really matter which point you pick in the small interval, right? Because whether you pick a psi 1 or some nearby point, the difference between these functions will be very small. And in the limit n goes to infinity, each of this interval is going to 0 anyway, right? So for continuous functions, this will make sense, right? Riemann integral will make sense. It will exist, okay? However, when you are going to enlarge your space to start including discontinuous functions, then it's not clear whether this integrals make sense. I'll give you one extremely violently discontinuous function, which is what is called Dirichlet function. Okay, there's a very violently discontinuous function, which is called the Dirichlet function. I don't know why he introduced this function, but I don't know what was his motivation. So this is equal to, say, 1 whenever x is a rational number. X is a rational number. And it is equal to 0 when x is irrational. Okay. Now you can imagine how violent is that, huh? Because I mean, you can, in any small interval, you can find infinite number of rational numbers and infinite number of irrational numbers. So even the small interval is wildly fluctuating, right? Okay. Now there is no way you can define Riemann integral with this, because just imagine to try to define the integral of Dirichlet function on this interval, right? Now, depending on, I could choose all this size to be rational numbers. If I choose all disk size to be rational numbers, then I will find the answer equal to 1 times the distance times the interval length. Whereas I could have also equally well chosen all of them to be irrational numbers, in which case I would get answer 0. Or I could choose in between, some of them rational, some of them irrational. You know, I can get any, I mean, it's completely arbitrary, right? There's no limit, right? So this function cannot be integrated using Riemann integral. So this is the problem here. I mean, if you want to have a closed, I mean, complete vector space, you are forced to include such functions. I mean, discontinuous functions. I don't say that we need to include Dirichlet functions, but this was just an example to show that the Riemann definition of integral fails. Okay. So then you are forced to also generalize that. Yeah.
May not be important, but when is Dirichlet function equal in its application?
I have no idea why this. I mean, maybe he just used it as an example for, you know, that, you know, that some things could go wrong. Maybe. I don't know if it had any application, any particular application. I don't know. Yeah. Maybe his purpose was just to show that, you know, this Riemann integral doesn't work. So I don't know. Or could be there something else, maybe. So what, I mean, so there is I'm not going to discuss in detail. I mean, actually, I will just state I mean, actually, if you are interested, you can look at these definitions. Lebesgue, it's called a Lebesgue integral. But I will not, I will just skip completely this, because in fact you will never need it. You know, you will never need in your quantum mechanics course or anything. Okay, it is sufficient to know that there is a definition of integral which generalizes Riemann integral. Okay, called Lebesgue integral, which can also handle even such violent functions like Dirichlet functions. And it gives an unambiguous answer, that definition of integral. So this can handle such functions also. I mean, even discontinuous functions like Dirichlet functions. The basic point about this is that one of the important reason why it can do this is that okay, let me just at least say a couple of words before, I mean, because this may look completely mysterious. I mean, what is this? So remember, I mean, so this was the Riemann integral definition, right? So what am I doing here? I do this, take the intervals here, and then I pick the value at each of these points, and then multiply these numbers and, you know, sum them up. Lebesgue is doing kind of complementing this whole thing. Well, what he says that let's fix the value of f. Okay. So for Lebesgue, what he does is that So suppose I'm given some function, again some interval a to b, some function. Now, okay, I'm just drawing a continuous function, but as I said, this will handle also discontinuous functions. But let's just look at the continuous functions. So what he does, he takes some value, let's call it fi, okay, and then consider a small interval between fi. So this is fi plus delta fi. This is fi minus delta fi. Okay, some small interval. So look at this. So look at this band. Okay, and then try to see what values of x, for what values of x the function is inside this band. Okay, so that is in this example, in this picture, it is here. You can see. Okay, is this right? So what he says, what Lebesgue does is that he says, okay, we'll define the integral like fi times the length of this interval. Okay, actually, what is more correct to say is that what Lebesgue does is that he takes this original, the full interval, and inside this interval he takes various subsets, right? And for those subsets he defines a measure, say length, notion of length. He defines a measure, and so what you're supposed to do is to take this value fi times the measure of that set. This will be some set, right? Okay. I mean, so the function could be, for example, like this. You know, in this case, you have also this part, right, in this set, because this all is in the same band. Okay, so say b is here. You have this band. So it may not be just a kind of connected. This set may not be connected to each other, right? Because there is this part in this picture. There is this part, this part, this part. For all of these values of x in these parts, the function is inside this band, right? So then you take fi times the sum of these measures, right? And then in sum over all these fi's. Okay? But in this way of definition, you see, it doesn't care about whether it is continuous or not. So the whole problem is basically reduced to defining a proper measure for all possible sets. I mean, and there is a definition of the Lebesgue measures. It's such that for continuous functions, both the Lebesgue and Riemann integrals give you the same answer, right? But for non-continuous functions, particularly those functions where Riemann integral cannot be carried out, Lebesgue gives you a definite formula. Okay? And the important point about this is that the measure, the way he defines the measure of any set, any countable set. You know what is a countable set? Is 0, is equal to 0. This is the important point of the Lebesgue measure. Lebesgue measure of any countable set. That set could have infinite number of points, but it should be countable. That's the important point. You should be able to countable, meaning this is my first point, second point, third point. There's a way to count them. Okay, but maybe the number of points is infinity. But see, there are two types of infinities. One is countable infinity. Other is uncountable infinity. Okay, so countable infinity is something where the elements of the set can be mapped to integers, to the natural numbers 1, 2, 3, 4, 5. Okay. Whereas uncountable infinity is the one which is where you cannot give a map to the integers. You cannot count them. Okay. So as an example, the set of rational numbers is countable. Okay. Whereas set of real numbers is not countable. Okay. So set of rational numbers is countable. Because you can arrange them in some particular order. You see, you can, for example, I mean, yeah, you can do like this. So you can take, so you start, say, between the interval between 0 and 1. Let's say, so I take 0, 1, then I can take 1/2, 1/3, 2/3. You know, there's a definite pattern I can give, and this is a kind I can count. I mean, you keep increasing the denominator step by step. And then the numerator, you go from 1 up to the maximum possible value, right? So this way you can count 4, 1/4, 2/4 is already there, so I don't count, 3/4. Then you get a 5, 1/5, 2/5, 3/5, 4/5, and so on. No? you can arrange them in a certain order, right? And you can map them. So this goes to the first number, second, 2, 3, 4, 5, 6, like that you can count. So rational numbers, although the number of rational numbers is infinite, okay, it's countable. But for real numbers, you cannot do that. There's no way you can, put something like there are infinite number of real numbers, which even, it's not possible to even start counting them. There's no way you can count them. So as a result, Lebesgue measure for the rational numbers is 0. So what it means, you go back to the Dirichlet function. Remember, Dirichlet function was 1 for the rational numbers and 0 for irrational numbers. So even if you had picked this fi to be 1, let's take fi to be 1, okay? Use the Lebesgue thing. The set, the x's for which fi equal to 1 is the set of rational numbers, but that has measure 0. So it doesn't contribute. Then when f equal to 0, the set of the set of x's for which f equal to 0 is a set of irrational numbers, which is a full interval minus the rational numbers. So the measure of irrational numbers is the same as the length. So this integral will give you 0 for the Dirichlet function. Okay, it's a well-defined thing. So it can handle all this such discontinuities. Okay, I think I will not say anything more. But if you are interested, if those of you are interested, you can just read it. Read this page 188. Page 188 is where they define what is the Lebesgue measure, how the Lebesgue measure is defined. But I think, as I said, you will never need it really. Okay, so now 3 o'clock. So okay. Now there is a very important theorem. So okay, what was the purpose of doing that? The purpose of doing that was to be able to handle more general functions, not just continuous functions, right? So that now we can define using Lebesgue integral the inner product also for such functions, right? Because the integral is defined. So then you can ask whether, those functions. So we define now the space of functions, which is denoted by L2W. Okay, this is the space of functions. Let's see, is that the definition? Let's see. Yeah. Also, let me put also the AB, the interval. So this is the standard notation. This is the notation which you will find in all math books. Okay. This is L2W. W is the weight. AB is the interval. Functions on the interval AB. Okay. And this is the space of functions which satisfy the condition f mod square Wx dx from A to B, but this is the integral in the Lebesgue sense, not in the Riemann sense. In the Lebesgue sense, if that integral exists, which means if it is less than infinity, is something finite. Okay, in that case, you say, so this is a set of all such functions. This set is a set of all functions which satisfy this condition. This is called square integrable. They are square integrable with this weight, but square integrable in the Lebesgue sense. Then that is the space, and the important theorem is that this space is closed. This is a theorem due to Riesch and Fischer. Again, no proof. You don't need the proof, but just the knowledge that this is true. Fischer. This must be a pretty difficult proof, I think. I've never gone through this proof myself. So Riesch and Fischer prove that this space, that L2WAB, is complete. In other words, if you give me some sequence of functions here, which satisfy the Cauchy criteria, right? Then it has a limit function. It converges to a function which is again in the same space. That's the important point. So let me just say this, because there is one point I would like to emphasize a little bit. So what we are saying is that so if there is some sequence is given fk of x is some sequence such that fk x minus flx mod square wx dx a to b goes to 0 as k and l go to 0 infinity. Okay. Then what this theorem says, Rees-Fisher theorem says, then the sequence converges to a function f, which is again in L2 WAB. So this what it means is, of course, that you have this integral fx minus fkx mod square wx dx is goes to 0 in the limit k goes to infinity. Right. How about, yeah?
So these are the two theorems for
Rees and Fisher, these two people together proved this.
So this one for complete
Yeah.
is it part of that?
This I'm just explaining that. I mean, what this means. I'm just explicitly saying what it means. Okay. But the reason why I'm doing this is for a particular reason. I mean, you can ask the question: is it unique? Is this function unique? Rees theorem says that it converges to a function f, right? Is it unique? I mean, it could happen that, I mean, so my question is, the question we are asking is that, could it be that it also converges to another function g of x, right? Well, if so, then the g of x, I mean, if this is the case, then g of x minus f of x integral must vanish, right? This a to b should go to 0, should be 0, right? But but this does not really mean that g of x equal to f of x. You see, because remember, in the Lebesgue integral, I mean, some sets may have measure 0, right? For example, the set of rational numbers, the measure was 0. On that, so I mean, these two may be different on a set whose measure is 0. Suppose that was the case. Suppose these two functions were equal in all the sets which had non-zero measures, right? But it was not equal when for those sets where the measure was 0. For example, say rational points. Suppose this g of x is not equal to f of x. It doesn't matter. Lebesgue integral doesn't see it. You see. So in some sense, what you have to do is you should not consider these two functions. You shouldn't consider them as two different functions. You should think of them as the same function, right? If they differ only in some set of measure 0, you should think of them as same function, right? The reason is otherwise this will not define. Otherwise, this inner product will not define you to a metric space, because remember, metric space was something which had to also satisfy the condition that if the distance between two vectors is 0, then the two vectors must be equal, right? But I mean, this distance is 0 because this is what how I'm defining as a distance. This is a distance, right? Distance square. Distance square is 0, but nevertheless, g and f may be different on a measure 0 set, right? I mean, take g of x equal to f of x plus Dirichlet function. Okay. Suppose g of x equal to f of x plus Dirichlet function. Then take the g of x minus f of x is just Dirichlet function, right? And we know that the integral of Dirichlet function using Lebesgue definition is 0, right? So even though this integral is 0, but these two functions are not equal. G of x is not equal to f of x, right? So what is it? We are saying g of x is equal to f g of x fails to be equal to f of x only in some set whose measure, Lebesgue measure, is 0, right? Because Dirichlet function, remember, was not equal to 0, was equal to 1 for the rational numbers, but the measure of rational numbers is 0, right? So this is an important point here, that in this L2 space you must identify, you must not consider them as two different vectors. Two functions which differ from each other only on some countable number of points, okay, whose measure is 0, whose Lebesgue measure is 0. Those two functions, you shouldn't think of them as defining two different vectors. Okay. This is correct also because, I mean, from quantum mechanics point of view, it's okay, right? Because after all, in quantum mechanics, we are interested in, okay, this wave function or whatever this, you have some state, right? But in reality, we are interested in computing observables, no, like expectation values of various matrix elements of various observables and so on. But in those things are written in terms of integrals, right? So if you have two different wave functions which differ from each other only in a measure 0 set, okay, that will not show up in your expectation values of any observable. So you should not consider these two wave functions as different physical states. They are the same state. Okay. So this is also motivated from physics point of view, the fact that you should not think of these two as different functions. So actually, usually it's called, I mean, in mathematics literature, it's called, so what the statement is, the way it's presented is that f of this sequence converges to some function f in this L2 space, right, almost everywhere, right, almost everywhere, which means that it may not be equal at countable number of set of points. Okay. When that happens, is that clear? So you say this converges to f of x in L2W almost everywhere, or sometimes it's also used converges in the mean. This converges to f of x in the mean. These are different in the mean meaning on average kind of, on an average it kind of converges there. Okay. This is to distinguish that this may not be exactly this function f, but it will be almost everywhere. It may fail to be equal at some set of points whose measure is 0. Okay, that's the point. Yeah.
If function W is not given, how can we choose this function?
No, that's given to you. I mean, a physical problem will pick up what W, pick your W, right? The weight function, you mean the weight function, right? Yeah, yeah. So that you see, that's already there in the definition of the L2 space. Obviously, when you choose different W's, you'll get different spaces in general, right?
So there is not a definition for W.
W is arbitrary. You choose. You know, the only condition on W was that it should be non-zero. It should be positive everywhere. And for each x, it should be positive. That was only, and continuous and so on. Okay. Apart from that, there is no other criteria. But in individual physics problems that you will be doing, it will come with its own W, right? Yeah.
What is the difference between the weight function and the determinant of the transformation matrix? Like, for instance, when
Yeah.
Cartesian,
True.
yeah.
No, that in that example, right? But I may say, well, I don't know. I mean, from where this W came. Okay, in that example I gave you from 3 dimension to go to the polar coordinate, that just comes from the Jacobian.
Was like the metric
Right.
matrix
Yeah.
determinant.
Sure. Yeah. That, in that case, yes. But I mean, I need not, right? I mean, purely from a mathematical point of view, I could just put anything, right? I could just define anything. I mean, there is no reason why it should be 1. I mean, 1 is again a special function after all, right?
Yeah, I thought it was like the Jacobian.
In general, in physics problems, that is the way it will appear. Huh?
Yeah.
However, this is even in physics, because the space, you see, I mean, because we are used to working on a flat space, Euclidean space. When you study, for example, Einstein's theory of general relativity, right? There, the space-time itself is curved. Okay, and in that case, indeed, there is a weight function. even without, I mean, in that case, there's no particular coordinate system because space is curved. There's no canonical choice of a coordinate system. So you have to define it in a way which is a general coordinate invariant and so on and so forth. So there are some weight functions there. But you're right. If you are working with the Euclidean space, in the Euclidean space, by definition, the weight is 1, right? But then, okay, you can, when you change the coordinate, it will induce the Jacobians, right, or the coordinate transformation. And let's see what else I can say. So this here. Okay. So now, yeah, few things. Weierstrass theorem I cannot prove today. Tomorrow. Okay. So now let us go back to the choosing some kind of a basis for this spaces. How can we choose? I mean, there are infinite dimensional spaces. So, of course, the basis will also have infinite number of vectors, right? So, see. Right. So, let's suppose I'm given some basis. I mean, some orthonormal basis. And I will call them again EI. Right? Orthonormal basis in the L2, in L2W AB. I mean, there will be infinite number of them. This is, of course, because this is infinite dimensional. So I will go all the way up to infinity. I mean, we will construct some examples later. But at the moment, I'm just trying to give a general statements here. And let's suppose there is some function, another function f inside element of this here. Okay. And so we can compute this. Let's call this. Let's define this term. The Fi is equal to the inner product, the scalar product of Ei with f. Okay. So which of course, I mean, this just means integral Ei complex conjugate f wx dx from A to B. This is the definition. Okay. So we define this, and then let us consider the sum of Fi Ei. Okay. Question is, you remember for the finite dimensional cases, when you compute this coefficient, I mean, let's go back to the finite dimensional case, just to remind you the first chapter. So suppose it was really n dimensional. Okay. Then this sum will go from I equal to, so you will define, so in finite dimensional case, so you have E1 up to En, some n dimensional space. In that case, again, you can define this quantity EIF, which is Fi, and then if you write down this combination Fi Ei, this is in fact the original vector f, right? How do you see that? Because, well, just multiply this by Ej. Yeah. So this is simply Fi Ej Ei, okay, which is equal to Fj, but that was a definition. Okay. So this gives you, I mean, what I'm saying is that, okay, forget this for the moment. Let's start from here. Since this is a basis, I can always expand f in terms of basis vectors with some coefficients. But this coefficient is in fact that, because that can be seen by multiplying by Ej, right? So you would then, so you can ask the question now, what happens in the infinite dimensional case now, in this case now, right? Is it still true that this is equal to f, right? So this is the question, is it equal, or in what sense it's equal, you know, etc. That's a question you can ask. And maybe here also I'll just state the theorem rather than proving this, because really most of this stuff you just need to know that this is true, No, but maybe I should prove one thing first. Okay. So let's do the following. Yeah. So. Right. So let's look at, so here, I mean, this is of course an infinite sum now, right? I mean, that's a bit difficult to handle. So what we can do is we can truncate this sum up to some finite number, okay, and then say a finite number k, and then take the limit k goes to infinity. So that way you'll get sequence of vectors, right? So we can define a sequence of vector, which I will call fk, which is simply obtained by taking these coefficients. I mean, these coefficients, once this is given and that is given, you can just compute it by computing this integral in principle, right? You can calculate. So these numbers are given to you. Now let's construct this sequence of vectors. So I take this number fi multiply by ei and take the sum I equal to 1 up to k. So there is for each k there is a vector, right? And then you consider this infinite sequence as k goes from 1 to infinity. You consider this sequence of vectors. Okay. Then there is a inequality that you can prove. That inequality is the following: that if you take this fi mod square and sum I equal to 1 up to k, okay, this is always going to be less than or equal to the length square of, I mean the length square of f. That you can prove, and this is called the Bessel inequality. Okay. So let me just, it's an easy proof. Let me just quickly go through that. Okay, so let us start from, take the inner product of f with this vector fk. Okay. Let's take that. Okay. And take the mod square of this. Then and use now the Cauchy-Schwarz inequality. Okay. But Cauchy-Schwarz inequality says that this should be less than or equal to the length square of f times the length square of fk. Right. So it should be times fk. Okay. So now let's compute these terms and this and that separately. So what do we get fk for with fk? Well, fk is by definition this. So fi ei, I going from 1 up to, so let me put the I going from 1 up to n. And then here, this also, this gives you fj bar, because it's a dual vector, ej, and j going from 1 to n. Right? Now you use the fact that this is orthonormal, so ej with ei is delta ji. I mean, these are numbers, so, ei with ej is delta ij. So one of the sums I can perform, right? I mean, only the j equal to I will survive here. So this gives you summed over I, fi mod square. When j is equal to I, this becomes mod square, and I goes from 1 up to k. Sorry, k. Okay, that is the right hand. I mean, this term. Okay. Now let's compute this quantity f with fk, but fk by definition is fi ei summed I equal to 1 to k. So I can take out fi. Then this f with ei was by definition fi, right? That's how we define. Actually, fi bar, fi complex conjugate, because fi was defined like ei with f, right? So, but here is f with ei, so it's the complex conjugate of that. So this gives you fi mod square, because there's already fi, and this with that is fi bar. So this is fi mod square, I equal to 1 to k. So, this is also the same, except that now here you have a square and there is only one term. So, this you can cancel one factor, and what is left over is sum over fi mod square is less than or equal to f with f. So, that is this equation. So, this is called Bessel inequality. Okay. Now, this is true of course for every k. This is true for every k, right. So, in particular this will also be true I equal to 1 to infinity fi mod square is also going to be less than or equal to f with f. Okay. Why is that so? Because okay, I mean this is true for every n, every k, right, is bounded by that, right. And you know that there is this I mean, so here you have this this is a monotonic sequence, right, because if you take the k plus 1, you are adding one more positive term. So, if you take the k sum or k plus 1 sum or k plus 2 sum, the value is increasing, right. It is monotonically increasing, but it is bounded above, and you know that such a sequence has a limit, right, and that limit is going to be always also bounded by that, right. So, first of all, this series indeed converges, right, so that you can really take k all the way up to infinity. This converges, it does not blow up, no, it converges, and that whatever the result is going to be less than or equal to f with f. Okay. So, this is what is called the Bessel inequality, this thing actually. Okay. What else I have to say here? Okay, so now what is the theorem here? So first of all, I need to define what do I mean by basis vector. Okay, because when you have infinite number of basis vectors, it's very difficult to say whether you have found everything, right? I mean, what do I mean by infinity? Infinity plus 1 is also infinity, right? I mean, so the definition that so you have to define somehow, right? I mean, how you define the basis. So definition is given in the following way. I mean, there are probably many different ways of defining this basis definition, but so the definition which is used in this book is the following. So E1, E2, etc. This set of orthonormal vectors is a basis if the only vector which is orthogonal to all of them all of the EI is the null vector. Okay. That's a definition. I mean, this is in the finite dimensional case, it's obvious. This is the definition, right? I mean, if you have a basis, then I mean, there cannot be any other vector which is orthogonal to all of them, because if there was any vector which was orthogonal to all of them, that vector could not have been expanded in terms of the original basis, because I mean this fi coefficient just obtained by this thing here, this equation, right? So suppose f was a vector which is orthogonal to all the EIs, then all the fi's would be 0, right? In which case when you rewrite f as a sum over fi EI, all the fi's are 0, so which means f is a trivial vector, null vector, right? Which so in the finite dimensional case is obvious. This is correct. This is a good definition, right? Infinite dimensional case, okay. So we just extend that definition all the way up to infinite dimensional case. We say that we use this definition. So what is the thing you can prove with this definition? Okay. So let's suppose that we have a basis in this sense. We have an orthonormal basis in this sense, right? That there is no other vector which is orthogonal to, no non-trivial vector which is orthogonal to all of them. So we choose that as a definition. Then the statement is that if you construct this FIs, I mean FI which are simply this what we discuss EI F, okay, and construct this vector, the sequence of vectors, which is I equal to 1 to k Fi EI. Then first of all, this sequence has a limit, vector, okay, and that limit vector, and it is in fact f itself. Okay. I mean, that is what you would expect for a basis vector, right? Because then for a basis vector, I should be able to expand that f in terms of the EIs, and that is what this statement is saying, that this infinite sequence of vectors has a limit vector which happens to be, which is equal to the f itself. Okay. So that's an important theorem. Okay. So, but in what sense? When you say in the limit point, is in the sense of sense that rho of f with fk goes to 0 as k goes to infinity. So in this sense. So I mean, this you see, this always, whenever you make such definitions using such limits, I mean using the length which uses the integral, right? The integrals are Lebesgue integrals. Okay. So really, when we say this converges to f, it's again in the sense that it's almost everywhere. No? Almost everywhere. It need not be exactly equal to f as at every point x, right? It may differ from that at some countable number of points. Okay. This can happen. Actually, we will see that even in the Fourier series, we will see that such things happen. Okay. Later, I mean, maybe 2-3 weeks from now. Let's see. Okay. So let's see. First of all, if you are saying that this sequence has a limit, first of all, let's check whether the Cauchy criteria is satisfied by this or not, right? So we can compute the distance between rho of fk and fl. Okay. Rho square. Let's compute rho square. It's writing the square root there. Well, that is nothing else, but so it's just fk minus fl, the dual vector, with the fk minus fl, right? Okay. And let's suppose that k is, I mean, again, if k is equal to L, this is 0 immediately, right? So the non-trivial case is when k is different from L, and let's take k to be, so one of them has to be greater than the other, so let's take k is greater than L. So what is this fk minus fl? If you look at this definition, fk, the sum goes up to k, for the fl, the sum goes up to L. So fk minus L will be the things will go the sum from L plus 1 to k, right? So this guy is nothing else but fi ei, where I goes from L plus 1 up to k, right? And then you take the same thing here, so it will become fi bar, fj bar, let's say, j going from L plus 1 up to k, and ej, right? That's what you find, this is equal to that. And then ej with ei is orthonormal, Kronecker delta. So one sum you can perform I becomes equal to j. So this simply becomes fi mod square I going from L plus 1 up to L. Okay. But this must go to 0, right? Because we already said that the fi square, the sum over fi square converges, right? So because it was bounded by Bessel inequality, it was bounded by the length square of f, which was finite, right? And it's monotonic. So this was converges. So for the one of the conditions of the convergence of a series is that the sum. Sorry, this is k again. I keep writing. The sum from L plus 1 up to k for sufficiently large L and k vanishes, right? Otherwise, it would not converge. So this goes to 0 because of the boundedness that this was bounded. Okay. So therefore, I mean, so since this is satisfying the Cauchy criteria, Ries-Fischer theorem says that there exists a limit vector, right? We haven't gone through the proof of that. It must be. I mean, I myself don't know how you prove that kind of stuff. So this implies the fact that this is 0 implies using Ries-Fischer that there exists some let's not call it f because we still don't know whether it's f or not, that there exists some vector g in L2 WAB, that there exists some g in L2 WAB. That's what Ries-Fischer theorem is saying, right? That this sequence will converge. This sequence fk will converge to some vector g in L2 W such that rho of g and fk vanishes as k goes to infinity, right? That was the statement. Okay, but we still don't know. I mean, this is guaranteed by this theorem, but we don't know whether this g is the same as original f that we started with, right? Now, so we want to check whether it's original f or not. So let's compute. So let's compute this g with ej, okay, and take the difference between fk with ej, okay. I mean, this is the same as, sorry, let me write it like this. So I'm taking g minus fk and taking its inner product with ej, okay, which is what I wrote before. I just opened the bracket. But now let's use the Cauchy-Schwarz inequality again here, which again let me take. So this is equal to, this is less than or equal to. I have this vector, inner product of this vector with that vector. So it will be the length. So it will be the inner product of this with itself, but that is by definition the row of length between g and fk, right? So this is the row of g fk, okay, times ej ei, square, times square, row square, and then with the ej. But this is 1. I mean, the length square of that's 1, so I can forget that. Okay. But this goes to 0 as fk goes to infinity. So we are saying that this goes to, I mean, so this is going to be less than or equal to that. So if the right hand side is going to 0 as k goes to infinity, left hand side is going to go to 0. That's the only way, right? So this will go to 0 as k goes to infinity. I think this is probably the last one. Okay. On the other hand, let's open this up explicitly. So what we are finding, g with ej. So let's just open this bracket, minus fk with ej. Sorry, I put here sometimes bracket, sometimes not. Okay. So what is this? Sorry. So somebody said something? No. Okay. So let's calculate this guy. Fk was, remember, so this is nothing else but Fi Ei, Fi is bar Ei with Ej, where the sum is going from I equal to 1 to k, right? I mean this term, I'm just looking at that term. But this is nothing else but this is simply f j bar. Okay. Which is the same as f ej, because f j bar was by definition that. Yeah. So I mean, again, assuming that k is sufficiently large. I mean, j is something. J is some. I picked up some j, but j is some finite number, right? No matter how large, 1,000, 1 million, whatever I take j, I can always take k larger than that. If not, you see, then this could, if k was less than j, then this would be 0, right? So for this, because this is Kronecker delta, delta ij. But if the range of I does not include j, that would have been 0. So I will take k sufficiently large. Okay. So that is this. So what we are saying, I mean, we are saying that this minus that goes to 0 as k goes to infinity. But this quantity is in fact, for in k goes to infinity, is nothing else but f ej. Okay. So we are saying that g minus f with ej is equal to 0 for all j, because this j was completely arbitrary, right? So we have found a vector which is orthogonal to all the vectors of the basis vectors. But then by definition of the basis vectors, this must be a null vector, right? So we are indeed seeing that. So this implies, using the definition of the basis vectors, using the definition of basis, that f minus j must be null, f minus g must be null. Which means f is equal to g. Okay. This basically proves the statement. So this basically gives you a, I mean, once you give me the basis, then it tells you how to expand any arbitrary vector f in terms of as linear combination of basis vectors. It tells you how to compute, how to write down those coefficients. Those coefficients were simply the this thing. I mean, the inner product, right? Fi was simply Ei with f. Right? So it gives you the method how to go about. Once you give me the basis, then I can compute this, and these numbers will be exactly expansion coefficients, because we are saying that that vector, this fk, converges to f. So I think that's the point here. And furthermore, you can show that, you remember there was a Bessel inequality. We said that sum over fi square, fi mod square, is always less than the length square of f. But in this case, actually it will become equal. Okay. And that you can prove again. So finally, the Bessel inequality becomes an equality in this case. That is what one is saying. So remember, so what this is proving is that this sequence of fk's converges to actually f itself, because g is equal to f, right? So again, the logic was the sequence of fk satisfies the Cauchy criteria. Okay. So Riesz-Fischer theorem says that it converges to some vector. We call that vector g. And now we prove that g is in fact equal to f. Okay. So that therefore this sequence of vectors converges to f. Okay. That means that the rho of between the length, the distance between f and fk should go to 0 as k goes to infinity, right? Because the sequence is converging to fk. So let's just calculate that. So let's compute. So rho square of fk is equal to f minus fk and with f minus fk. Sometimes I forget to put the bracket here. Okay, this, right? That's a definition of that. So let's open this up. Yeah, we have to open this up. So there will be, I think some of the things I had already worked out before, but anyway, I erased maybe. Anyway, so this will be, we have to open up. There are 4 terms. F with f, that's f with f. And then you have, say, plus fk with fk. And then minus fk with f minus f with fk, right? 4 terms. Actually, we had worked it out. Now it's not in the blackboard, but anyway, let's just repeat that again. So what is, first of all, fk with fk? I think this was, do you remember this? I mean, this was simply fi square mod square I going from 1 to k. You remember that? I mean, each of them you write, this fk is fi ei. So when you take the inner product of this with itself, you will get fi ei with fj bar ej dual, but ej with ei is delta ij. So you can sum j, j will become equal to I, so that's that, fi mod square. So this is that. Now what about taking this f, say f with fk? So f is already given here. So f with fk is simply fi, and f with ei, but that is fi bar. So fi mod square. And again, sorry, there's a sum here, I equal to 1 to k. So these are all equal. And if you take the other way, it's just a complex conjugate, but this is real anyway. So these 2 terms add up and cancel with that because they are all equal. So therefore, this is equal to f with f minus summed I equal to 1 to k fi mod square. Okay, but we are saying that this goes to 0 because we said that this converges to f. So therefore, this length square goes to 0. So in k, as k goes to infinity, this must go to 0. But as k goes to infinity, this sum goes from I equal to 1 to infinity. So we are saying that f, the length square of f, is in fact equal to the full sum fi mod square from I going from 0 to infinity, 1 to infinity. Okay. So that's saying that it is saturating the Bessel inequality. It saturates, which means the equality sign is applicable here. Okay. So if something doesn't satisfy, if some combination doesn't satisfy the equality in the Bessel inequality, which means suppose this was really less than that, that means that you are missing some, you don't have the full basis. You have missed some another orthonormal vector. You have missed it. Because it's difficult. See, it's infinite dimensional. You may, how can you know that you have taken care of all the orthonormal vectors, right? So this would be one check. I mean, okay, I think I'll now stop here.